Okay, so today we're going to discuss exponential objects in a category and functors, which I've mentioned before are the morphisms in the category of categories, right? So they're kind of like category homomorphisms. I wasn't quite sure whether to do functors first or exponentials because they're kind of related to each other in a way, but let's just go with the exponentials first because you're familiar with the universal properties from last time, I'm sure. And once again, if you have questions, just go ahead and type them right in the chat as I'm going, and I'll answer them as I go along. Okay, so an exponential object, I'm just going to give away the punchline, so to speak. It's the function type, right? So in Haskell, you have function f defined like that in Haskell, right? That a arrow b means that it's a function from the type of f there is a function from a to b. So like the products and coproducts that we looked at last time, the exponential object may not always exist given any two objects. And it's defined, when it does exist, it's defined by a universal property that we've seen before. So I'm just going to go ahead and start writing out the universal property. The exponential, so this function here is a function from a to b. The way we'd write that in the category as an exponential would be the object, and the parameter type, as you can see, is in the exponent position there, and the output type, the return type, the codomain, is in the base part of the exponent. And we'll see that this behaves. The reason for this is that it behaves the way you might expect with your products and coproducts or sums. And there's some isomorphisms there, right? But let's talk about what the universal property is. So if we have b to the a here, that's a function from a to b, right? And I'm going to move this over. Whoops. Move that. There's a function here from a to b. So if we have this function and we pair it, still not used to the whiteboard. we take the pair name. So we have this type here is pairs of an element of a and a function from a to b. That's all we need to actually evaluate that function, right? So we have a morphism from this object, this product, we'll call it eval, and that just goes to b, obviously. Okay, so here's the universal property. Let's say we have some other object, c, take the product with c with a, and there's a function from c times a to b. Let's call that f. Now, the universal property states that the universal property of the exponential states that there exists a unique morphism from c over here. This is a different object than c cross a, right? To b to the a. All right, let's call that, I'll just call it U for universal. All right, and you can draw the product over here between these two. Right. Oh, I should mention, I think when I talked about the product earlier, I used this notation to represent the pairing of functions. I'm just going to go down here for a second and draw out what I mean by that. So when I defined the product, this is just a notation issue. I should have done it differently last lecture. But we have the product AB, our objects A and B, some object X. We have our projections, some arbitrary functions, right? And then we know from the definition of the product there's a unique morphism there. And I think what I did last time is I wrote this as F times G. And obviously this is not the same thing that I wrote up here, right? It's because this is from an arbitrary object, and this is actually from a product. So what I'm going to do is I'm going to write this as with an angle brackets. So I'm going to do F G, right? And then I'll write for F or the times notation here. I'll do it like this. That'll mean the following morphisms. We have AB and CD, and let's draw our other objects. Say we have a morphism here, F, morphism here, G. We have our projectors. Right? So we have a we can compose these two to get a morphism from A times B to D and a morphism from A times B to C. That means that there exists a morphism like that, and I'll call that one F times G. Right? So yeah, essentially the universal property of the exponential object, and if you're just joining, the exponential object is essentially the function types of our category, has this property, right? So if there's any function from a product, C times A, to B, which is the codomain of our function, there exists this unique morphism from C to the exponential, such that this triangle here commutes. So in other words, F equals eval after U times ID of A. All right, so that's the universal property of our exponential object. But let's think about this a little bit. So I'm going to write out some function types here in typical Haskell notation. Let's say we have a function f c a to b, right? So that's a function from a pair CA to B. That is, you know, like a function with two arguments, essentially. But in Haskell, we write it differently, don't we? You usually write it in the curried form. Don't we? So this is essentially a function that takes an argument of type C and returns a function from A to B. And so essentially the universal property of the exponential object basically is just currying. You take this function with two arguments here, C times A to B, and you can convert it to this function U over here, which is a function from C to the functions from A to B. Right? And since you know, the products are commutative, you can just switch these around and, you know, make a function from A to C to B, right? So that's the exponential type, and we know what it is for our type theory, right, in Haskell or other functional programming languages. Those are the first class functions. In set, the exponential object exists for all pairs of sets. It's just the set of functions. So that actually does mean that set is locally small. Right, we talked about that. If the collection of morphisms between two objects is a set, then it's locally small. And if, you know, the collection of morphisms between two objects in set is a set, because set is locally small, that means that that corresponding set is the exponential object in the category of sets. That's good. All right. What else? In prop, our category of logical propositions. Let's move over here. Make some room. What would that be? So if we have an arrow A to B in prop, that's like a proof that A entails B. So the exponential object is essentially the proposition A implies B, right? And this is, I mean, another way of thinking of the objects in prop. They're not just the propositions themselves, but they could be sets of proofs of those propositions. So in this case, you have a set of proofs of B with the, you take A as a premise and B as a conclusion. You have some set of proofs. Then that the corresponding object in our propositions is the proposition A implies B. Right? What else? Are there any other exponential objects that I wanted to give examples of? I don't think so. Oh, in category, the exponential object in the category of categories. I think when I wrote this before, I had the, I wrote it like C, D is the functor category of functors from C to D. We're about to talk about functors right after this example, so it's a good segue, so to speak. I should have written it back in lecture 1 as C. So those are the functors F from C to D, right? And of course, the functors between two categories form a category themselves. So the category of categories has all its exponential objects. And there's one further definition that I'll add. If a category has, let's say, if a category is Cartesian, remember that's if it has all finite products and an initial object, and has all tuples, then it is a and if the category is also co-Cartesian, right, that's where it has all finite coproducts and an initial object, then we call it a bicartesian closed category. So closed essentially means that it has the exponential objects, right? And so these bicartesian closed categories are sort of what we want to have in our type theory, don't we? Because we have ways to combine, to make pairs of objects. We have ways to have the coproduct, which is like the combination of two types, just kind of mashing them together into one, right? And we have our function types. But so that gives us a lot of power already. But what we're going to see here is we're going to talk about functors now, and functors give us a lot more power for our programming language. Now, essentially, what a functor is it's like a container for a type, right? You can think about it that way for programming, right? So if you're familiar with Java or C++ generics, you can have a list of integers, or you can have a list of strings, right? So essentially, these are two different types, but we've essentially parameterized these by another type. So integer, int is a type, string is a type, and you can have, I think it's actually integer in Java, but never mind. So you can sort of generate new types from existing ones, and that's essentially what a functor is. Now, a functor is actually more restrictive than just being able to generate new types from existing ones, because they are the morphisms in the category of categories. They have to preserve the structure of a category. So what do we mean by that? Well, let's draw a category here, C. Their category. You've seen this one already. Draw a big circle around it. Oh, jeez. It's hard to draw a circle with this tablet. That's messy, but it'll do. Okay, and here's our functor. Sorry. There's F, and that's going to D, right? And what it's going to do, it's going to map the objects A, B, and C to other objects in D, which, they could be anything. I'm just going to write them as if they are the image of our functor here. So we have F of A, F of B, and F of C, right? Those are the objects that it maps, objects in D that the functor F maps the objects in C to. But a functor doesn't just map the object, it also maps the morphisms. So we have a morphism here. And by the way, these are just arbitrary, right? I mean, F of A and F of B could be the same object. It could mash them down together, right? And for that matter, there could also be other objects in D that are not in the image of our functor. But anyway, so we have it maps G to some morphism from FB to FC, and it's going to map the composition of G and F to a morphism from F of A to F of C. I'll draw a big circle around this guy too. Okay. My tablet's too small. There we go. All right, but there's one final, so we know that, so our functor maps the objects, it maps the morphisms. There's one final restriction, and that is that it has to preserve composition. Right, so let's go here, say, so is equal to That looks just like the requirements that we had for our monoid homomorphism, doesn't it? Right? And there's a corollary to this. For any object A, the identity maps to the corresponding identity. Right. And that just follows from the fact that the functor has to preserve composition. Okay. There's our functor. Let's look at some examples of functors. Do I have room? Here we go. Let's see here. Okay. Examples of functors. Oh. How about, so we've seen right here, right? We've sort of been able to, I mean, this isn't quite a functor because it actually takes pairs of objects instead of single objects, and pairs of morphisms instead of single morphisms. But one way we could solve that is, what if we just made, the product, I'll write it like this. Those little dashes inside the parentheses represent the fact that that's where our parameters go. We could just say that that's a functor from the product category. So the product of C with C to the category C. Looks good to me. And I'm not going to prove that, but I'm not going to prove that this is a functor. But one thing that we can do that is actually relevant to us as programmers, because when you're programming, you pretty much have to just stay within your category of types, right? So if you go over to the category of monoids or topological spaces, you're not in your category of types anymore, which is a problem. But as we'll see later when we study adjoint functors, we can sort of avoid that problem in a way. And how we're going to avoid it in this case is just by saying, okay, well, let's fix some object in C. So we have the functor, let's just say it's A, right? And so we take, essentially this takes an object in C and maps it to the product of that object with A. And this is a functor from C to C. Now, a functor from any category to itself is known as an endofunctor. And those are nice to use when you're programming because you never leave your category of types, right? And so this maps, like I said, it maps the objects to the product of the object with A, and it maps a morphism. So if we have a morphism F, it's going to map, I'll say that this is a morphism from B to C, right? That's going to map to I'll say what this is. All right. Looks good to me. And there's a name for this in Haskell. It's called the writer functor. I think it's like this. Yeah. I might be messing this up. Oh no, this is right. Okay. Let's like this. So I've changed what A stands for here, right? So in this case, we're fixing S in this, which it looks like this is taking 2, but essentially the actual functor would be writer S. And the way you actually define that this is a functor, because this is, when you define it like this is just a type constructor, right? It's saying here's a way to get 2 types, and it returns this other type. And so you give it a type S and a type A, and it returns the writer of those 2 types, right? But the way we define a functor in Haskell is like this. Shoot, I think that actually might be. So this is essentially saying this type constructor. So we've essentially partially applied our type constructor in here, so that we get another type constructor that just takes 1 type and maps it to a writer. And we're saying that that type constructor is a functor. And we're going to define a function here called fmap. Now, fmap in general is, I'll just write out the type of fmap. It takes a function. This is how we're going to map functions to other functions with our functor, right? It takes a function and it returns. I'll just write the general form. So f is a functor, right? That's our general form for fmap. So this in our case, when we're instancing our writer, we're defining fmap for our writer. That f would be replaced with just writer s, right? So how are we actually going to implement this function? It's going to take an f. Oh shit! You know what? I should have written this down beforehand. I'll give you another example of implementing the fmap in a second here, one that I've actually written down. So, okay. And you might be wondering why this is called writer, right? It's just a pair of types. Well, this particular way of, it turns out that the product functor we talked about here has some other additional properties that we're going to talk about later when we talk about adjunctions and monads that let us handle side effects in our programs. So let's talk about another example of a functor in Haskell. Well, we just looked at the exponential object, didn't we? And in fact, let's go more general in categories that may not have an exponential object but are still locally small. In general, we can say, okay, so if we have objects A and B in our category, I'm going to move all this down so we don't get distracted. You have an object A and B. A bunch of arrows, right? These arrows form a set. So we should think that there's a functor with 2 arguments, right? From our category C. This is C here, right? Oh, jeez. I really should stop trying to draw these circles. Anyway. Well, let's call this, actually, let's fix one of the objects, right? Let's fix the domain. See what happens, okay? So if we have I'm going to define a functor, call it ham A. This functor is a functor from C to sets. And essentially what this does, it'll take our B here, and it's going to map our B to the set of morphisms from A to B, right? We've fixed our A there. And if we have a morphism O F, sorry, B to C, this should map to a morphism in set from the ham set I'm going to write it like this for a second. I'll write it like this. A, B, running out of room. Ignore that line. I did that wrong too. Oh my God. It's A to C. There we go. I have the chat and everything off to the side here, so I can't see it, but you guys can still see it, I think. Right? And now, this looks like you could just compose it, right? If you have a function, essentially it would just be you compose f with your function from A to B, and then you get a function from A to C. And that is, in fact, how it works. Let's actually look at how that works with the exponentials, right? So if we have, if you want to stay inside your own category, we have our, you can fix the base of our exponential, and that's a functor from C to C. And we have, it maps, you know, an object to the exponential of A to, so we have an object B, it will map that object to the exponential A to the B. And it will map a morphism, F to C. I promise I won't take so long to draw it out this time. That's going to map to a, I'll just write it like this. Now you can verify that this works, right? That there is a way to actually find this morphism using the universal property of your exponentials, right? Given some object here. I don't know if I've written this down beforehand. Let me see here real quick. I did not. Oh, I did. Okay. Okay, good. Wait, no, I didn't. Okay. So it sort of makes sense, though. You can just compose a morphism, right? And you would end up with your with this sort of thing. But there is a way to prove, I think maybe I'll have this as one of your exercises for the homework. Yeah, by the way, your exercises for this week, I will not be able to put them up tonight because I haven't figured out quite yet what I'm going to do for exercises with functors. But it will be up by tomorrow night. So sometime tomorrow I'll put up the assignment for this week. So that's our function between exponentials, and of course there is a version in Haskell called the reader functor, and this time I actually do have the implementation for it written down. Now, so the interesting thing about this is just a bit of Haskell notation. Another way you could write this is like this. You could use the prefix notation instead of the infix. Right? And that's convenient because essentially what we can do when we're actually declaring this as a functor, we can partially apply it, right? And this time I'm actually going to type out the type of fmap explicitly, even though you don't have to do this when you're implementing it. We have a function a to b, a function s to b, and then now looking at this, look at this for a second. It looks like it's just a composition. And as we've seen, that's essentially what it is. And the nice thing about Haskell, there's a really simple way to, I'll write it the long way first, but f and g are our two functions that we're mapping. Right, that's, the obvious way to do it. There's a much cleaner way, or maybe that's less obvious. You could just write right. You're essentially saying that the fmap function for this functor is just the composition function. It's pretty cool. That's the nice thing about Haskell is that sometimes when you're defining a function, you don't even need to refer to the arguments of the function at all. Hold on a second. Okay. Sorry about that. So that's our reader functor, and you can kind of think of this as, it's weird to think of, can you guys still hear me? Yes, you can. Okay. You kind of think of this as like I said, you can kind of think of these as a container for your types, right? But it's weird to think of a function as a container, right? That seems more like a process. But in functional programming, there's no real difference between your data and your programs, right? In fact, when I was working with Clojure a lot, one of the cool things you can do in that is you can just use a dictionary. A dictionary is this sort of hash map type in Clojure. You can just use a dictionary in any place where you would use a function. So the parameter essentially is the keys for your dictionary, and then it returns the values, right? And obviously, Clojure is dynamically typed, so you don't have to worry too much about what the actual keys and values are. And it's also not a purely functional language because if you're putting in a dictionary, sometimes it's just going to be there won't be a key for the value that you're actually using. But that's nice, especially if you're writing tests. So you can think of a dictionary as a function in Clojure. Can you think of a function as a sort of data structure? Well, maybe. I mean, a list you can kind of think of as a function from integers to whatever values, whatever type you have in the list, right? And that's just, the index function. Or you could just say, have a function from integers to some type and call that a list if you want. But I'm kind of just, shooting the breeze here. Let's actually talk about lists, right? Here's an example of a list function, and this is maybe where the fmap comes in is sort of the most obvious. Here's how list is implemented in Haskell. Let's look at what's happening here. This is a type of structure. It takes one value. That's our type. And remember, I said the bar is kind of like it means that this is it's either nil or it's a cons. So nil would be your empty list. The cons is either is the A and then a list of A's. I'm sure you know what a cons is at this point. But let's write our fmap. F So this underscore here means that we're essentially ignoring what the function is because you can't return it. If you're mapping over an empty list, it's just an empty list, right? It doesn't matter what the actual function is that you're using. And, usually one of the first things you encounter in terms of functional programming is the map function, right? Where you have a list and then you can, map a function over the list. Well, fmap is kind of a generalization of the map function when you think about it. And I'm essentially implementing the map function here, but it applies to any functor, and list is a function. So the second part of fmap here, we're going to write equals look at that. Very clean. So this is an example of pattern matching in Haskell, where the second argument of fmap is a list of A, right? And the first argument is a function from A to B. So the list can either be nil or it can be a cons A, and then L would be another list of A. So I've essentially defined this recursively, right? The value of fmap for cons AL is just another cons, and we've applied the function f to A there, the head element of our list, and then we apply fmap f to the tail of our list, right? And that's our recursive definition of our list functor. There's one more I want to talk about, and this is the maybe functor. Very simple. In fact, I would say, I just want to point out, this has a really easy to understand way of describing it in just a category. If A is the type here, which I'll write as a capital A because we're talking about categories again. Right? So it's either an element of A or it's an element of 1, our singleton set, which you can kind of think of like that. In this case, we're interpreting that singleton element as null, right? And that essentially is what the maybe functor does. In, say, Java, every type, well, except for the primitive types like int or char, every type so the type of integers or strings, it's not really the set of all integers or the set of all strings. It's the set of integers as well as null, right? Or it's the set of strings as well as null, right? So, and a lot of times you just kind of ignore that when you're writing a Java program. You just assume that that the string is actually the set of all strings, but it's not. Those are not functions, mathematically speaking, because if you pass in the value null, which is a valid string in Java, it's going to blow up unless you specifically, say this is what I want to do in the case of null. But you can't do that in Haskell. This string type is literally the set of all strings. There's no null there, and same for integers. But the maybe functor here kind of gives us a way around that, and it gives us a way around that that's actually a lot more powerful than the null in Java because we have fmap, remember? So you can write your functions that are just looking at your strings or integers or whatever they are, and then when you run into the issue of, oh, actually maybe maybe there are nulls here, right? You can fmap those functions up to a function from maybe string to int or whatever you want to do, right? An example would be, say, actually, I'll save that example for next time. But I'll just describe the fmap function for maybe. It's another example of pattern matching. Right? So if our value is nothing, then it just returns nothing. It's kind of like doing a null check and then returning null. You just throw the null up to whoever's calling you and let them worry about it, right? Alternatively, boom, very simple, right? Very simple to implement, and now you have this functor, which essentially lets you write code ignoring the case where it's null, and then reuse that code in the case where you might have to deal with nulls. So functors are very powerful. We're starting to get into this space where I'm going to open up Q&A in a second here. We're starting to get into a space where we're abstracting a little bit more over our categories, and we're talking about morphisms between categories now, and it's going to get a lot more abstract a lot faster. But the benefit of that is that we can start getting more and more powerful tools to use in programming, right? Before we had, like singleton sets or pairs and stuff, and those are useful certainly, but we're going to get more powerful things. And the advantage of category theory is that it lets you sort of ignore the implementation details here and just talk about what's going on with your objects and morphisms. And so you can sort of start to reason about what's going on with your types on a little bit higher plane, and then bring that down to your code. And it's very useful when architecting complex systems. So let's open up Q&A here. you guys don't have any additional questions, I'll just let you go. Hope you've enjoyed. Again, the assignment, Keith. Oops, I'm sorry. I think I just want to mute you there. Do you have a question, Keith? Oh, he left. Okay, well, I guess that's it for today. Thank you all for coming. Like I said, the assignment's going to be out before tomorrow night, sometime maybe mid to late afternoon. I'll see you all next time. Bye.